And it's a great pleasure actually to introduce Mario Mori. He's a professor at Current Institute and works also with Google. And yeah, he's been contributing to learning theory and machine learning for many, many years. Yeah, I'm very happy that we have him as a speaker here talking on learning bounds for multi-class classification. Please enjoy the talk.
Okay, thank you, Marius, for the introduction, and thank you for inviting me. Yeah, so this talk, let me just say, you may have heard a precursor of this talk if you attended this same workshop last year, but this is sort of like a plus version of this, hopefully. So the talk's title is Learning Bounds for Multi-Class Classification, but I could also add Structured Prediction, and this is joint work with Corina Cortes, who is Director of Research at Google New York, Vitaly Kuznetsov, who used to be a PhD student of mine, but who is now also working at Google, and Scott Yang, who used to be a PhD student, and despite what it says on the slide, who is now working at DISHA. So let me start with the motivation for this work. The motivation is both, as the title suggests, multi-class classification, but perhaps in the hardest problem of multi-class would be structured prediction. And the problem is, can you derive learning bounds that are meaningful and insightful for both of these problems? And in particular, one of the problems that people have been interested in the past is the way, particularly for this workshop and its theme, how these guarantees vary as a function of the number of classes, okay? Which clearly in the structured prediction case is quite large, but even in many problems tackled in standard multi-class, quite large, as again the theme of this workshop suggests. So let me start with structured prediction, and then I'll talk about the consequence of this for multi-class. For structured prediction, by definition, the output admits some structure, which means that the set of labels, capital Y, can be decomposed into the cross product of substructure sets, Y1, Y2, Y sub L. And similarly, the loss function can be decomposed along those substructures. So a simple example is the Hamming loss, where the loss of two sequences, for example, or images, can be decomposed into the sum of the losses per patch if it's images, per word or per position if it's sequences, and typically, but not necessarily, averaged. Okay, so it's 1 over the number of patches or length of the sequence. Another interesting loss function widely used in natural language processing and many other areas is the so-called edit distance, which computes the minimal number of edit costs, the cost of edit operations to go from one sequence, Y1, YL, to another sequence, which might not even have the same length, Y prime 1, Y prime L prime, I could say. So examples of such tasks in natural language processing are, for example, pronunciation modeling, where here you see, for example, at the top of the slide, a sentence in English, I have formulated A, and you see underneath the corresponding phonemic transcription. And clearly the way that you would want to measure the difference between two labeling would not be just 0 or 1, whether you got it all correct or not, but take into account the loss per each one of the perhaps syllables that you have been transcribing. Similarly, for part of speech tagging, probably one of the simplest structural prediction tasks, for each word you would want to label, each word which should be labeled with a tag, determiner, noun, verb, as you can see in that example. And more generally, for context-free parsing, that's the problem of assigning a tree structure to each sentence. That is shown here, for example, for the same sentence. Again, clearly there is structure in the output. And then similarly, again, for dependency parsing, where now the structure is not a tree, but an acyclic graph. Okay? Similar examples exist in computer vision tasks. For example, semantic image segmentation is a classical one, where on the left you want to decompose or label that image with the part that corresponds to a horse, the part that corresponds to a human, or human pose estimation, where you try to estimate the pose and the angles, and there are lots of degrees of freedom for humans, as you know, that correspond to a particular image, in this case, that of Nadal, the tennis player, okay? So for all of these structural prediction tasks, typically the family of, the way the problem is tackled is via a family of scoring functions. So you have a family of functions, capital H, that maps x times y to r. Said differently, for any input x, say an image or a sequence, there is a function that assigns a score to a possible element labeled y in capital Y. Okay, and the typical way that this is used is that the prediction for a particular input x is done via this function that I denote by, I don't know, straight h, which assigns to input x the label that has the largest score, the y that has the largest h of xy. For many of these problems, it is critical to decompose the function h into typically a sum of functions. This decomposition is typically done via, or can be represented very generally, via a factor graph. A factor graph simply just denotes what this decomposition is about. So in the top example, that of pairwise Markov network decomposition, you see that there are two orange nodes. That means that the function can be decomposed as a sum of two functions. One corresponds to f1, little f1, and that says that f1 is corrected to 1 and 2. That means that it's f1 takes as arguments, in addition to the input x, y's that are, say, y in position 1, the label in position 1, and the label in position 2. So that could be like, for example, the diagram. And similarly, at position, the f2 is the one that takes as arguments y2 and y3. And that's what all that the graph is indicating. So that's the diagram y2, y3. There are many other possible ways of decomposing the function. Another decomposition is indicated via another factor graph there, where you see that now the first function takes arguments y1 and y3, and the second one, all three of the y's, okay? The choice of the decomposition is really a matter of the intuition and probably prior knowledge about the task. So the factor graph can typically be viewed as a graph capital G, undirected, where V is the number of vertices, F is the number of these orange nodes, and E is the edges. And for any F, any of those functions, the neighborhood of F is denoted by capital N, and Y, capital Y sub F is the cross product of the substructure values, what the argument of that function can take as values. So said differently, in simple terms, a function h of xy can then be written as a sum over f in capital F of h sub f of x comma yf, where yf is an element of that capital YF. More generally, you can have factor graphs that are example dependent, and this is the most general case that I will be considering. That means for each input x sub I, you might have actually a different graph and different decomposition. So you would have capital GI with its corresponding factor graph VI, FI, EI, okay? All of this being said, let me just consider some simple cases that people use in practice, in particular that of linear decompositions and linear hypotheses, and more specifically, linear decompositions of the features. For linear hypothesis, decomposing the feature function as a sum is equivalent to decomposing the function as a sum. So if capital phi of xy is the feature function, if you write it as a sum of phi functions, little phi functions, then clearly h of xy can also be written as a sum of functions, each one of them being w dot the little phi's. And the example here for a bigram decomposition, if you look at the sentence, here the sentence is his cat ate the fish. The feature decomposition here is the one that takes position s, here position 4, as an argument, and then it takes as an argument two elements y3 and y4, which is the bigram at position 4, if you want. Okay, so that's the V and D tags in this case. Okay, so again, feature decomposition for linear hypothesis is essentially equivalent to function decomposition. Let me say a few words about loss functions. There are many loss functions, some of which I just described at the beginning. I will make very few assumptions about loss functions. In particular, I will just assume that the loss function is bounded by some upper bound capital M. And I will also assume that the function is definite. That means that if the loss of y prime is 0, then y and y prime coincide. Okay, this would apply to a variety of different loss functions, including those that I mentioned, such as eddy distance or Hamming loss. But it would also apply to a family of other loss functions that's much broader, that of tropical losses, or it would apply to the blue score loss, or n-gram losses, or rational losses. Most losses that you see in practice would have these properties. Okay, so these are really mild assumptions. The structure prediction problem then is the following. It's the one that consists of a particular supervised learning problem where the learner receives a labeled sample x1, y1, xm, ym, where the y's are, y sub i's are in capital Y. And the problem consists of finding a scoring function h that maps from x times y to r and that admits a small expected loss. Okay? So, of course, the question here, and this has been a question for a while, is can we give learning guarantees for structured prediction? In particular, this comes up because if you think of the number of possible ways of labeling, even in part of speech tagging, which is a simple task, there are, say, typically for languages such as English, French, Italian, or other languages of this kind, there are, say, about 50 ways of choosing a tag at each position. If the sentence has length just 10, that's 50 to the power of 10, right? So there are lots of different possible labelings. The number of classes then is extremely large, right? So is it possible to learn even when the number of classes is so large? Some natural questions that come up, you know, fundamental learning theory questions is how many samples would I need in order to learn in such cases? Would I actually be able to learn with a polynomial number of sample points, right? So these are the natural questions. So this drives me to the theoretical questions of structured prediction with the standard observation, of course, that standard multi-class learning bounds that have a dependency on the number of classes could not be applicable in this case, since they would be exponential in the number of classes. And then a few words about previous work, at least previous work for the general case of loss functions. There's been work by Ben Taskar et al. A few years ago with interesting bounds based on covering numbers for the specific case of the Hamming loss and linear hypothesis. And then there's been a series of bounds that are packed Bayesian bounds. That means typically for randomized algorithms. Given by Dave McAllister. Those are more general in a way that they can apply to more general families. But the question that comes up is, can we derive learning guarantees for general hypothesis sets and general loss functions with the few assumptions that I made before? So one way to tackle these problems is via what we have defined as being a measure of complexity, that of factor graph complexity. So, if you're familiar with the notion of Rademacher complexity, you can think of this as being a generalization of that notion. So the empirical factor graph complexity of a hypothesis set capital H of scoring functions can be written as follows. It's 1 over m, the expectation of over a family of coins, epsilons, epsilon i's, that are independent coins taking values +1, -1, uniformly at random. of the sum over the number of examples, I from 1 to m, sum over the number of orange nodes in that factor graph, sum over the little f, and sum over all the possible arguments values y in capital Y sub f. Of what? Of coins that are labeled by I, f, and y, that's epsilon I, f, y, and h sub f, which is the function, one of the functions you have in the decomposition of h, at xi, and value y, y being one of the elements in capital YF again. So if you rewrite this, you can think of this as the expectation of a supremum over the choice of h of 1 over m, an inner product. So as this inner product is the inner product of a vector of random noise, because these coins have been chosen uniformly at random, their values, and a vector of scores, which are the scores given by each one of these functions in the decomposition, modulo a factor that is a normalization factor. That's a square root of fi. If all the fi's were equal, you could just take this normalization factor out of the complexity. So what does it say? It says that it's a measure of complexity because if you could match with your hypothesis set closely any kind of a vector of random noise, then that would sort of mean that you can match random noise with your hypothesis, therefore your hypothesis set is very, very rich. Okay, so it's the same sort of notion of Rademacher complexity extended to the case where you have this decomposition over factor graphs. And as in the case of Rademacher complexity, this was for a fixed sample. The expectation of this quantity over all possible samples is what we call the factor graph complexity. Okay? All right. Now, I'm going to present to you a number of margin bounds for structured prediction, and next I will talk about multi-class, but before doing so, let me just remind you of what the notion of confidence margin corresponds to here. For an input x and labeled with y, the rho sub h of x, y, y prime is the minimum. Actually, you don't need a y prime in the third argument of rho sub h is just a typo. It should not be here. So the margin at xy is simply the minimum difference of the score of the desired label y and that of a runner-up. Okay, the runner-up is the best y prime you could choose. So of course, if there is a y prime that has a larger score than the score of the desired label y, this quantity would be negative. So in fact, there is an error when this margin is non-positive. Okay? And so even when there is an error, when this quantity is small, you could interpret this as meaning that the classifier has small confidence, which is the reason why we talk about confidence margin. In structured prediction, we have different ways of taking into account the loss function when talking about the margin. And so the notion of empirical margin loss can be used as both in an additive fashion, which is what is shown up there, and in the multiplicative fashion. Both of these notions would coincide with the standard binary case in the binary classification case. So the function phi sub m is indicated in the plot in red. The expectation here, when I write x comma y according to S, is simply the empirical expectation over x and y. So say, for example, if I take the multiplicative version, so the second definition, when it's negative, when the quantity in the argument of phi sub m is negative, that means that 1 minus that difference of scores is negative. That means that actually the prediction is necessarily correct, so the loss is 0. But even when the loss is still correct, but small, this loss function phi sub m would, as in the case of other margin bounds, penalize the function in a linear fashion from 0 to capital M. M here is the upper bound on the loss. Okay? All right, so we have been given generalization bounds for structured prediction in terms of the empirical margin loss that I just introduced and the factor graph complexity notion that I presented before. And these are the form of these bounds. The first one is in terms of the additive empirical margin loss. The second one in terms of the multiplicative. You would see that both of these typically are very similar, except from the fact that capital M shows up in the second term for the multiplicative one, which is natural because the loss is multiplied by that. So you would have to have that factor appearing. These are the tightest margin bounds for structured prediction. Additionally, they're data dependent because these complexity terms can be estimated, as in the case of standard Hadamard complexity. These bounds, in the special case of what was studied by Ben Tasker, improve upon those bounds. Okay, in fact, improve not just by a log term, but even in a much stronger way. Okay. Technically, the way we are deriving these bounds is via a contraction lemma, which, for those of you who are familiar with the way that you use these kind of things for Rademacher complexity, there's a well-known Talleyrand's lemma as a contraction lemma. This, technically, the contraction lemma that we use here is a generalization of that lemma, which helps us give much finer results. Okay. Up to here is essentially what you may have heard in the same workshop last year. But we have actually also derived an even better contraction lemma. That's why I call it a contraction lemma plus, which therefore is an even better result, finer result. Technically, let me tell you why this is difficult, right? It's difficult because by nature, the form of the result is an argmax. It's the argmax of a bunch of scores. So when you have to compute the Rademacher complexity or upper bounded, you have this margin function phi sub m that applies to the both a function of the loss, which is additive or multiplicative, and an argmax. Okay, so this actually is one of the reasons why all of these complications arise. How do you actually manage to use the Lipschitzness of the function phi sub m in this case, and how do you then manage to upper bound this in terms of the complexity that depends on the hypothesis set? I won't go into the details of this, but all I want to tell you here is that in this case here, this bound tells you that there exists a distribution U that you see in the second expectation, and that distribution U is just only its existence that we would be using. Okay? All right. So I'm going to be a little bit more precise now. Suppose that you take the special case of linear hypothesis, which is the one used by most structured prediction algorithms, actually. So in that case, it's the family of functions that can be described as mapping x comma y to w dot psi of xy, where psi of xy is the feature function associated to x and y. And typically with a norm sub p of w bounded by lambda p. In the same way, I will denote by r sub q the norm, the maximum norm of the feature vector, where q is the conjugate of p. 1 over p plus 1 over q is equal to 1. Okay. So if you take this kind of, these definitions, here are the learning bounds that we're giving for structured prediction now. These bounds, I'm going to discuss basically, say, the additive ones, because I've already said what is the difference between the additive and multiplicative in each case. If you look at them, the critical term here is the complexity term. The first term is the standard margin bound, empirical margin. What is remarkable is the way the size, the average size of the factor graph shows up here. So you have a square root of 1 over m sum of fi squares. You can interpret this as the average size of the factor graph. This shows you to what extent the size or the average size of the factor graph is crucial for generalization in structured prediction. Additionally, as you can see, this learning bound does not otherwise explicitly has any dependency on the number of classes. Okay? Neither does it even have a dependency on the number of possible categories at any position, let's say if you're doing structural prediction, part of speech tagging, or anything else. Okay? So this is remarkable. This absence of dependency on anything else, essentially, than the size of the factor graph. In the past, people have been discussing learning or guarantees for structured prediction in multiple different ways, but surely this has not been sufficiently emphasized. The size of the way you're factoring, how do you factor that function becomes really, really critical. Okay? This is for a norm 2 bound. In the norm 1 case, you find something similar, somewhat more favorable, because instead of being just the average size, you can even have a sparser average, depending on what those functions, the feature values psi sub j are, which, for example, in natural language processing, they tend to be extremely sparse. So you might even have not just the sum over all the i's here, but the sum only over those that are non-zero. So it's even more favorable. More favorable in that way, less favorable as is standard for norm 1 bounds, that there is a log of the number of the dimension that shows up here, log of the two times the dimension of the feature vector or the weight vector. Okay? Same sort of sparsity bounds. You notice here that if I just drop the S, you actually see really, really familiar generalization bounds for those of you who have seen this before. This is all for structured prediction bounds. Let me re-emphasize. These are the tightest bounds for structured prediction. Okay? The specific case of structured prediction is multi-class, standard multi-class classification. I'm now going to present to you some learning bounds for that case. And again, since I've already, so maybe I can answer that later on summary. So since I've already been discussing the difference between additive and multiplicative bounds, margin bounds, I'm not going to go through this again. I'm just showing you the results for the additive case. For the additive empirical margin loss for multi-class classification, you get the following margin bounds. They should be very familiar. Let's say, for example, for the norm 2 case, the second line, the complexity bounds only depends on lambda 2 R2. Lambda 2 is the bound on the norm 2 of the feature vector. R2 is, R2 is the bound on the bound of the feature vector. Lambda 2 is the bound on the norm 2 of the weight vector, divided by the square of m, or the margin. There's something missing here, no? This bound must be incorrect. The number of classes does not show up. It is correct. This is the tightest bound for multi-class classification, margin bound. It is tight. It actually syntactically matches what you get exactly in binary classification. Okay? It does not mean that it is magical. The number of classes should show up somewhere, but it does not show up any more explicitly. Where does it show up? It shows up intrinsically via the norm 2 of the weight vector, or say the norm 2 of the feature vector. Because clearly, if you want to describe accurately a multi-class classification problem with a very large number of classes, something in the feature vector has to depend on these different classes. So if the norm 2, the norm 2 would have to depend on these number of classes. Clearly, the same kind of things in the norm 1 case, and you recognize there again, syntactically the same margin bounds as for binary classification for norm 1. I've listed there also in the third line the norm 1, 2. I could do any other group norm in the same way. You would essentially find the same familiar bounds for binary classification syntactically. Okay? The consequence of this is that, the sort of questions that could have come up naturally, which is, how does the number of classes play a role in this sort of bounds? Basically, at least its explicit dependency has completely disappeared. I'm saying this because over the years, I have been deriving bounds that have been depending linearly on the number of classes, square root of the number of classes. Other people have done, and we have done also, logarithmical number of classes. All of these are gone, okay? So let me just quickly say a few more words, and then I'll answer questions. There's a whole family of consequences from this sort of guarantees, but in particular, you could try to, for the structure prediction case, try to learn by controlling the size of the factor graph, right? This is one of the key ideas there. Here, you have to control, of course, as usual in a way, the norm, and whichever norm you think is familiar, is relevant for your problem of the weight vector. Quickly, I want to tell you that all of these results generalize to a much broader case that I have been talking about in the last few years, where your hypothesis set is extremely rich. It's extremely rich, but it can be decomposed, partitioned into a bunch of hypothesis set, H1, H2, H sub P. And the functions, the scoring functions that you will be considering there would be convex combinations of functions from these different hypothesis sets. Everything that I said up to now can be generalized to that setting, which is the setting that I call the voted risk minimization case, with learning bounds that then depend not just on the factor graph of those hypothesis set that form the partition, but also on the amount of mixture weight you assign to each one of them, explicitly on those. These are, I think, the finest bound that could be used in a variety of practical cases for, say, structural prediction and multi-class. And we have actually experimented with those by deriving algorithms based on this sorts of guarantees. So I'm not going to go through those details a lot more. I want to quickly conclude by saying that these are this is a general theory of multi-class classification. Technically, I told you that the role that those contraction lemmas are playing is really, really crucial. These are tight margin bounds for both structure prediction and standard multi-class. They hold for general loss functions. They're data dependent, so those quantities that I mentioned earlier on could be actually estimated. For structure prediction, the size of the factor graph is playing a key role, which I think is important to take into account, really. And I mentioned that these guarantees extend to the case of voted risk minimization, VRM theory. We have derived new algorithms, struct boost, VCRF, V is for the voted case, that benefit from favorable performance results. And in general, these guarantees can help derive better algorithms because they're based on a better understanding of the problem. Okay, so I'm going to stop here. So since Samori was impatient to ask his question, go ahead now. Oh, I see. Yes. So same answer as for. So the question, if not everybody heard it, is this type of results on margin bounds in general. They assume that you first choose a confidence margin, some constant rho, then you give a bound, and then of course the question is, can you give a bound that holds uniformly over all choices of rho? And the answer is yes, straightforwardly using the same sort of technique that. One would use also in binary classification. Essentially, it's just turning the crank. So yes, the answer is yes, but it doesn't require too much work technically. What would that add? Oh, so it is at the price of a additional term, same usual term, which is of the form square root of the log of R over rho, where rho is the rho that you have, and R is the upper bound on any possible margin that you could have, which could be capital M actually here. Okay, but it's exactly the same as what you get in the usual cases. It could additionally, by the way, you can generalize these bounds to the case where you don't even do margin bounds of this kind, but you do this kind of things that Kolchinsky and Panchenko consider, where instead of the standard margin losses and empirical margin losses that I showed you, you consider other families of function. That can be done in the same way here as well. Okay, so long as they're Lipschitz.
Actually, I have also a little question. In your structured result ++ on page 19, I looked into the proof, and the distribution U depends on epsilon, the indices V.
The indices?
Yeah.
Okay, so the indices U depend on epsilon?
Yes.
So
I was wondering how you then managed to apply this result because of this dependency. It seems not straightforward.
So you have to tell me which indices and which is it in this contraction lemma?
Yes.
Or
yes.
So in this contraction,
the indices to the right, V, M, J. They in your proof I found they depend on the epsilon, so I couldn't really figure. I mean,
so actually,
so
actually they do not depend on the epsilons. They do depend. They're depending on each other. Okay. This distribution capital U is not a distribution of independent coins here. These coins are dependent, but that dependency is actually not playing any role because, as I said, the critical observation here is that this expectation over U, over this distribution U, you can just replace it by a maximum. Okay, for many of the bounds that you, without even, I mean, you could even do something finer, but for the analysis it will be quite difficult because this distribution U is very difficult, very complicated. But it suffices that you just replace it with a maximum to derive all the bounds that I showed you. Okay?
Okay.
Yeah. Any other question? Yes, over there, I think. Okay, so this is a standard theoretical question. Can unlabeled data help? And can it help algorithmically? Can it help theoretically? And I think for binary classification and many other problems, actually, this has been studied quite a bit. There is this standard or pseudo-standard assumption of the so-called clustering assumption. If there is something like a clustering assumption, then I can show you. So the clustering assumption essentially says that points that are close to each other typically have the same label. Okay? If something like this, which is a distributional assumption, does hold, you can show both for the scenario of semi-supervised learning and transductive learning that you can derive actually even more optimistic bounds, even better bounds. The problem that I have, of course, with those kind of cases is that this is a hypothesis that is not testable, right? So unless you have really very strong prior knowledge about a task, it's a sort of a difficult thing to. If you have knowledge, yes, and the answer is yes, you get better guarantees.
Okay, let's thank our speaker again.
Thank you.